Okay, so for the first part of this video, I left off on part A and B, I believe. We did the motion diagram. Do remember with the motion diagrams, be as specific as you can with the displacements, the velocities, the times, make sure all of that is labeled on there. And then we also, through finding the motion diagram, we found out where the particle's turning point was, right? We knew that it happened at 2 seconds, but because the area underneath this curve was 10 meters and we knew we started at 30 meters, we knew that it then turned around at 40 meters, right? So it turned around at the 40-meter mark. So gave us a lot of information to work with, and hopefully wasn't too bad. Part C asks at what time does the particle reach the origin? So we are curious, when does the particle get back to not just its original starting position of 30, but when does it make it all the way back to the original position of 0 meters as opposed to just 30? So if we use this graph right, you could actually figure out, so again, this area was positive 10. Well, once we pass through the turning point here at 2 seconds, if we just follow out the area of this triangle here, right, once this area of the triangle balances the positive area up here, so if this was negative 10 meters down here, I know I'd end right back at 30 meters. But again, that's not what the question's asking. The question wants us to know how far do we get, or at what time does the particle reach the original origin. So rather than breaking it up like this and then figuring out how much more area I have to go the remaining 30, what I would recommend is starting at the turning point. So I'll get rid of all that little work there. So starting at the turning point, since we now know that the turning point is 40 meters, we just need to figure out how far do we have to go past 2 seconds here. So how many seconds do we have to go past 2 seconds before the area under the curve is 40? Okay, so you can do kind of just a little bit of guess and check work with that, or however you're comfortable. But in this case, if we did go over to 4 seconds and down here, once again that would only be negative 10 meters. So that's not enough. So if I go all the way over to 6 seconds, right, if I go over to 6 seconds, that would give me a base of that triangle of 4. And then if I look for the height of that triangle, the height of that triangle would be negative 20. So the area of this triangle would be 1/2 4 times negative 20, which is negative 40. So what that tells me is this is, right, negative 40 meters of displacement. So that takes me right back from the furthest turning point of 40 meters back to the origin. So conveniently, this graph actually happens to end when we reach the origin. So after 6 seconds, we would make our way back to the origin. Now we're going to see using calculus in a few minutes here how we could actually have done this a different way. But in this case, you could have kind of just done some guess and check work by using the area underneath the curve. And again, just figure out when the area takes away our furthest displacement here and takes us back to 0. Hopefully this makes sense. If for some reason either of these 3 parts here didn't make sense, just let me know and I'll see if I can help you guys beyond that as well. Okay, so this page leads us to the basics of integration. And I talked with you guys briefly in class about this as well, so you've seen a little bit of a preview of this. But I would recommend, and you guys are obviously welcome to even pause the video here if you would like, but I'd recommend writing down this equation, and then I'm going to explain exactly what everything on here means. So if you would like to pause the video so you can do that, and then I'll talk, that's fine. But otherwise, just write this down, and you guys can either do that and listen or come back to that. The one thing that I am going to change on here is going to be, they use TI in our textbook to say the initial time, but I still tend to use T sub 0, and the AP board tends to stick with T sub 0 as well. So I'm going to go ahead and change all of those to T sub 0s instead of TIs. But other than that, most of these variables will be pretty similar to what we've looked at. Okay, so again, if you want to pause this to finish copying down, that is fine, and then listen when you're ready. So once you've got this and you're ready to roll with it, let's just break down what this means. So that fancy symbol there, that's just truly the integral symbol. So when you see that, and again we talked about integrals a little bit, but it's just the opposite process of the derivative. Okay, so when you see that symbol, that's telling us to integrate. Now the dt here is telling us what we're integrating it with respect to. So what I mean by that is if I gave you a function like this, let's just start simple. If I gave you the integral of x to the third, I would have to tell you dx, because otherwise, if I didn't integrate it with respect to x, I would just be adding in a new variable, and I'll show you what I mean by that in just a second. Okay, but let's first look at what we would actually do to integrate. Well, I said integration is the opposite of derivation, right? So derivation, you'd bring the power out front, and then you would reduce the power by 1. For integration, you increase the power by 1, but then you divide by that new power. So I would increase this to 4, but then I would divide by 4, so I would have 1/4 x to the 4, or you could have obviously x to the 4th over 4. The other thing we have to be careful about is when you integrate, you actually don't know if you have a constant term, right? And so what I mean by that is if I was doing the derivative, if I had x squared plus x plus 5, I know that the power of 2 comes out front, the power of 1 comes out front, but what happens to 5, right? It completely disappears. So when I integrate, how do I know if there was or wasn't some constant term over here? Well, the truth is, unless I have some context, I don't. So the way that we account for that, and you guys may have seen this already in calc, but the way that you account for that is you throw in this extra plus c. So c is just representing any possible constant that we may or may not have had. Okay, so this is a pretty straightforward integration. So again, this is just how I integrate x to the 3rd power. Now I said it's important that it's in terms of whatever variable I'm using, because if I actually gave you x cubed and then I gave you with respect to dt, this would be saying integrate it with respect to t and not x, and since t is a different variable than x, when I do this I would basically just be adding in, because right here I can think of this as t to the 0th power. So I'd be increasing that to t to the 1st power. I'd bring the 1 and divide the 1 out front. But the x cubed would almost just be like a coefficient. So it's very important that the dt or dx matches whatever variable we're working in. Because of that, when you see this u here, this u is just representing any function of x, or in this case, obviously we're using t. So the u is just representing any function of t. So again, another example of that would just be if I had something of the nature of maybe t cubed plus t squared plus 5. Maybe I've got something that looks like that. So I would just define this whole thing as my u, and then I would integrate each one of these with respect to t. So then the other two things I want you to notice about this are the t sub 0 and the tf. What that is telling us is what range of time or what range of values are we integrating this with respect to. And what I mean by that is, if I gave you a graph, right, we know that we'd find the area under the curve, right, but you want to know how much of the curve you're looking at. So if I gave you a curve like this, these two, the ti and the tf, tell me basically where am I starting and where am I ending, because it's only this much area of the curve that I'm looking for. Okay, so for 99% of the time in this course, they'll give us the time frame at which we're looking at, and that way we know the specific area. Because otherwise this function could go on indefinitely and there wouldn't be a definite integral. There wouldn't be a defined area. So that's what all of this process helps us do. Okay, so the integration really just truly helps me find the area underneath the curve. So let's look at maybe a specific example of this. So I'll go ahead and kind of work through. Let's just use this. So this is my original function, and then let me say that I want to integrate that from 1 to 3 seconds. Okay, so I've got t to the 3rd plus t to the 2nd plus 5, and I want you to find the integral from 1 to 3 seconds. Well, again, the first thing that we would do would be we would just find, using the opposite of the power rule, I would just find the new function based on that. Okay, so I would increase the power, and then I would divide by that new power. So 1/4 t to the 4th. I would increase this power to 3 and then divide by that, so plus 1/3 t to the 3rd. And then the 5 would gain a t, because again I can think of this right now as t to the 0th power, which would increase to 1, right? And then I would divide by 1, but obviously that doesn't do anything with 5. And then I would throw in my plus c for good measure. Now again, most of the time in context, and we'll see exactly how, but most of the time in context you'll be able to get rid of the c or plug in the specific number. And you'll see what I mean hopefully pretty soon by that. But then this stage of the formula up here, this stage of the equation, says we're listing the intervals down here. So what this may look like, now sometimes you may see this as a bracket, sometimes it may just be listed as a straight line. But because our book uses just a straight line, I'll try and be consistent with that. I think calculus you might actually use a bracket, but anyway. So again, I'm just listing 1 to 3, and this is telling me what range of values I'm going to work with. So then if you notice the last stage here of this equation, The last stage is saying I'm plugging in the final time, so I'm plugging in the upper bound, then I'm just subtracting when I plug in the smaller bound. So I'm taking this new function that I have, which is this whole mess down here. I'm plugging in the upper time, and then I'm plugging in the smaller time, and I'm finding the difference between the two. Okay, so again, let's kind of finish out with this. I'm not going to leave you completely alone on that. So I'll help you work the rest of the way through it. So in this particular function, I would start with 1/4. So instead of t, I started right t there, but instead of t, I would plug in 3 to the 4th because I'm plugging in the upper bound. Right, so I'm going to start by plugging that in, plus 1/3, again plugging in the upper bound, so 3 to the 3rd, plus 5 times, instead of t again, 3, and then plus c. And then I would take this and I would subtract from this the entire function, so I'm going to throw some parentheses around it because I'm doing this whole function again, except this time when I plug in 1. So 1/4, 1 to the 4th, plus 1/3, 1 to the 3rd, plus 5 times 1, plus c. Now the important thing I want you to notice here is look at your c, look at your constant. Does it matter what number that constant is? Well, since I've got c, but then I'm immediately subtracting c, right, it truly doesn't matter for the purpose of the integral. It doesn't matter what that original position was. Okay, so at this point, I'll leave it to you guys if you want to calculate it, but truly you would just calculate each of these and then subtract each of these, and you would get your numerical answer, so we'd get whatever the number is. And that number would represent, again, the area. So again, that would represent the area from, in this particular case, from 1 to 3. So that would represent the area under this curve from 1 to 3. Okay, or actually under this curve, which we integrated to find it. Okay, so I know right now it seems a little bit abstract. You will talk about this more in calc, and so I'm not going to go into too much detail beyond this. I just want to give us kind of a working idea, a working understanding of what it means to do integration. So like I said, you'll go into a lot more detail with calculus. This is going to be about the extent to which we need to be comfortable in physics, but we'll see obviously a number more of more involved examples. So then the second thing down here, the second equation down here, all I want you to realize from this is just giving us u and w as two separate functions in terms of dt. So I could almost actually even go up to that first example I gave you, t cubed plus t squared plus 5. You could think of this to where we define u as t cubed, w as t squared. All this equation is saying is if you want to find the integral of this whole equation, you can just do them in separate pieces as long as you can break them up as the sum. Okay, so I could, again, just like I did up above, I could do the integral of t cubed, which would be 1/4 t to the 4th. I could do the integral of t to the 2nd, which would be 1/3 t to the 3rd, and then I could do the integral of this, and then just sum all of those up. Now again, you guys can start to imagine, for instance, we know that sine of 2t, right? If I gave you this as my function, and I asked you to find the derivative of that, right? How do we find the derivative? Well, the derivative of sine is cosine, right? So it'd be cosine of 2t, but then because we have the 2t inside and not just t, we'd actually have to do the chain rule or use substitution, and we'd have to find the derivative of the inside as well, which is, in this case, would be 2 if we were doing it with respect to t. So my final answer here would be 2 cosine of 2t. The reason I mentioned this, I know this goes back to derivatives, but you can imagine if I give you a function that looks something like this, it might be a little bit trickier to go back and integrate it. So we'll see some examples where it is maybe a little bit trickier to go back in integration. And you guys could imagine maybe even something like the product rule or the quotient rule. Those can get pretty complex pretty quickly. So you guys will do much more extensive work with that in calculus than we will in here. Right now, the basics that I want you to be comfortable with are the power rule, and the opposite of the power rule for integration. We will deal with the other integrals as they come up. So we'll deal with some of the sine, cosine functions as those come up later on in the year, but I don't want to overwhelm you right now with too much of this new material. So just kind of keep it a balance. So I'll go ahead and pause here. I'll pick up with the last example or two from this section of notes in the final part of this section.